Hey everybody, and welcome back to Algebra 2 online. So the plan for today is just do some review problems from this unit. I'm going to kind of cover a bunch of different things, and I want to start off with one of these because these are probably the most missed things I feel like from this unit. And the reason they're probably missed most often is because the domain part. So remember, whenever you're solving an even root equation or inequality, you really do want to think about where that thing is defined, right? You might get like things in equations where you solve it all out, but then the answer or answers you get are not part of the solution. Or if it's an inequality, you may be getting some sort of restricted inequality answer due to that domain. So I want to start off and just do the domain part of this. So we need z minus 2 quantity squared to be greater than or equal to 0. And if you think about what that one looks like, right, we got a quadratic over there, and it's an open up quadratic, and certainly everything in here is greater than or equal to 0. So the domain is actually all reals, which is nice. So if you graph this thing, everything would show up somewhere. It'll be defined everywhere. So that's actually nice. So whatever we actually get as an answer to this problem will work as the actual answer. Like, we won't have to actually restrict anything here. So to solve this thing, I'm going to start off, just do, I'm just going to move that 4 over. And then raise both sides to the power of 6. And then you have to, I don't know, I'm having a hard time with writing right now. Squared, there we go. Square that thing out, you'll get z squared minus 4z plus 4. And then if you put everything on the same side, I would move it to the left just to keep everything positive. And so we get another quadratic inequality. This one, I would just do quadratic formula because the c is so large, so I wouldn't bother trying to factor it and things like that. If you do the quadratic formula, you get negative 62 and 66 as the roots. So if you think about what it looks like, you got negative 62, 66. We got an open up quadratic like that. And we want to know when is it less than 0, right? Which is the part down here. And specifically, we want less than 0. So we don't want to include the roots, right? So it's basically like, strictly less than the x-axis there. So the answer would just be anything from negative 62 up to right before 66 there. So strictly in between those two roots. And there's no reason to restrict that domain or anything. That answer is perfectly fine because we did the domain check over here. But that's it. All right, so want to do one of these kind of rational equation problems as well. Remember that when you see something like this to the 2/3, that is two things. It is a polynomial of power 2, and then a cubic function, a cubic root function, right? So the 2 tells me I should get 2 answers, and the cubic tells me, basically mostly just I know I won't need to check my answers. Whatever they are should work because they're odd. It's an odd root function, which is well defined. All right, so I'm going to start off. If you add 6, right, you would be at negative 50, and then we can divide by negative 2. So we would have 25 equaling negative 1 minus 42m raised to the 2/3. And then at this point, I always recommend just getting rid of the cube first, or the root first. So here I would get rid of the cube root. So if I cube both sides, you would get 15,625 equals negative 1 minus 42m squared. And then a lot of times when I solve out these quadratics, I multiply this all out, combine terms, right, and try to factor or do quadratic formula. I'm going to do it a little different than I normally do. So we know that like, so if you have like something squared equals 9, right, then there's two things you can square and get that 9. I'm basically going to do the same thing. The plus and minus square root of this number would be what would square to this negative 1 minus 42m, right? So I can basically use that idea. And plus and minus 125, if you square them, you get 15625. And so those two things are what negative 1 minus 42m would equal. And that's just using like this idea, okay? If you don't want to do it that way, you don't have to. I'm just showing you a different way to solve a quadratic. You could just multiply this all out and combine like terms. And then it's kind of nice because it kind of leads to these two paths. So if you do, let's take the positive one over here, and then the negative one over here. So we're going to add 1. We get 126. And then divide by negative 42, and we would get negative 3. And then here we're going to add 1, get negative 124. And then divide by negative 42. And I don't think that's super nice. I think we're just going to leave it as 124 over 42 equals m. And you don't have to check because it's a cube root. They should both work. We got two answers like we knew we should because it's a second degree polynomial. But yeah, so anytime you see any of these weird rational exponents like that, if you saw, I don't know, 11 halves, you would need 11 answers. And because it would be a 2 on the bottom, you would need to check your answers. That's an important part. All right, so one of the things I see, sadly, as a common mistake in this unit is if I gave someone this problem, let's say, as a first step, people would go to this. So if you look at what that is, okay, let me just kind of group this so you see it a bit better. So basically, we just took this root inequality and just dropped all the roots, okay? And then from here, you could get x is greater than negative 6 if this was true, but this is not true. Sadly, I still see it, and I know I said it in a previous video, but it's always good to say it a few times. If you think about it, it just breaks the scale of how we do math. You know, whatever we do to the left side and the right side at the same time. And what we're doing here is if you wanted to do this trick, you're doing something twice. You're doing the exact same thing twice on one side and then once on the other. That's not how this works, right? The only thing you can do here is, and this is what you would do, you have a square root. We're going to kill it with a square, but then we just have to square the other side. But then it is kind of annoying because it's one of those things where you have this whole thing and you'll have to double distribute. Like the right side is really nice, but the left side is not. So you would have to like distribute that, and you're still going to have a root in your answer. And so this is one of those root inequality problems where you'd have to like kill off the root twice. It wouldn't be gone like right away, okay? But that is a common mistake. Don't want you to make it on the test. You can't do something twice on one side and once on the other. It literally is the same as like if you have x minus 2 equals 3, and you're like, okay, I want to add 2 to get x by itself, but I'm going to add 2 twice over here. That is no longer true. That then x would equal what? 7, right? 7 minus 2 is not 3. And that's what you're exactly doing if you try to kill this and this and this. You're not going to be able to get all the roots gone. You have to do it in 2 steps, basically. All right. So this was just, one of the first things that we kind of saw in this unit was these simplifying like radical expressions. And they're always just like good practice with like algebra, and so I wanted to do another one. We had that weird one where it was like the whole thing equaled 0 once you simplified it. So here, This is like some kind of made-up work that I have here, and there's 3 mistakes, and what I would recommend you do is try to find all 3 mistakes in here. So like pause the video and try to think about that. I am going to basically tell them to you now, so if you haven't paused it, sorry. All right, so one of them is in here. Okay, so what they did is they probably combined the 2 cube roots there. But what they did that's wrong is they probably thought that was cube root of y to the 48, right? 6 times 8. Because then the cube root of y to the 48th would be equal to y to the 16th. That part would be true, but this part is not true. The way you combine powers, right, is you add them when they're multiplied like this, right? If you have like x times x, that's what it means to be x squared. You don't multiply 1 times 1 and say that equals x to the first, right? So you add them. And so that's one mistake. Another mistake is kind of right in here. So that 7 is strictly outside the parenthesis. So the whole parenthesis here, this whole thing is raised to the -2, so that can pop down there and be a positive 2 on the bottom. But it shouldn't include that 7. That 7 should stay on top. This 7 in the -2 is 49 on the bottom. Well, 7 to the -42, sorry, is 49 on the top. And so you would basically have 49 times that 7. That 7 should just stay up there. That's another mistake. And then the last one is right here. So z squared in there, like if you do z squared and the whole thing was squared, then you multiply here. This is where you multiply. So you get z to the 4th, 2 times 2. All it is just z squared times z squared. And we just talked about up here, you add. So you add there. 4 is kind of a weird number because what it multiplies to and adds to is the same. But if it was z squared cubed, it would be z to the 6th because you multiply, and it's just because you have z squared, z squared, z squared. And you add up 1, 2, 3, 4, 5, 6 z's. But that's it. Those are the 3 mistakes. That should have been a 4, not a 1. For some reason, it was a 1. All right, so another important part in this unit is just finding a domain of rational expressions, okay? And so this one right here, if we start simplifying just a tad in the beginning, it would be 16 over the 4th root of 256x minus 10. The -1, right, just flips it onto the bottom. And so there's definitely 2 things that could happen, right, because we have a fraction. We could be dividing by 0. So let's just put that over here and divide by 0. The other thing that could happen is you've got an even root. And if you have an even root, you're going to have to be careful about that part too. So the even root part, you can just always take the inside and set it greater than or equal to 0. So 256, x is greater than or equal to 10. X is greater than or equal to 10 over 256. And then for the divide by 0 part, right, if you 4th root 0, you'll get 0. So you just need 256x to equal 10, right? So if x equals 10 over 256, that's like what we don't want to happen, I guess, right? Because that's the one time where this thing would be undefined on the bottom for the divide by 0 reasons. So then you just kind of, in these problems, right, you look at both things and you think about how those combine. And you need to be greater than or equal to that 10 over 56, but you also can't be 10 over 56. So it gives you a domain of strictly greater than 10 over 56. All right, so this one is just kind of a cool, looks messy, but turns out to be not so messy sort of problem. Just a radical inequality kind of thing. So I'm going to start by getting the... All right, so for this one, we'll just kind of start off, and we can kill a lot of these roots, right? We have the 40th root on both sides, then there's a square root we can kill on both sides. So the first thing I would do is really just realize it's the same problem as this one, okay? And then for that, we're going to square both sides, right, to get rid of the root on the right. We have 9x squared plus 6x plus 1 greater than 50x plus 6. If you move everything to the left, you get minus 44x's minus 5. If you do like quadratic formula here or something, you'll see that the roots are 5 and negative a ninth, right? And so, again, just done a lot of these this year, but always good to graph them again. So we got a quadratic inequality pointing up. We want it to be strictly greater than, right? So we're talking about that part or that part. So the answers to the inequality look like they're x greater than 5 or x less than a negative 9, a ninth. But those would be wrong if you just leave it because domain, right? So you have to think about the fact that you got even roots here. We need that, really we have a lot of even root domains to check. Like for the 40th root over here, right, we need the square root of 3x plus 1 to be greater than 0. But then if you square both sides, you get that 3x plus 1 is greater than 0. So x is bigger than negative a third. And if you do the same thing over here, the first few roots will always just cancel off. So really we can just check when is that 50x plus 6 greater than 0. So that would be when x is bigger than negative 6 over 50. All right, so now the game becomes like just compare your solution space to where it's actually defined, right? So this one, bigger than 5, definitely is bigger than these two negative numbers. So that's good, right? And less than negative a ninth, though, is going to become an issue, right? Because you could be at like negative 100, and that's not bigger than these domains. So you have to be careful with that, all right? And we could even compare these two because we need to make sure that whatever x we plug in works for everything, right? So you need to take the more restrictive thing always. And so since this is a smaller number than this, right, we don't even want that one. This is actually all that we will compare, those two numbers, right? So, they kind of tell you what the inequality is. You want to be bigger than that, but less than that, right? And this number is smaller than this. So you basically get a kind of and inequality from negative 6 over 50 less than negative a ninth. And then that region works. But then you also have an or inequality, right? And you also get this, I'll just do it like with a comma. So you're also in this region where you're bigger than 5, okay? Which is a pretty weird answer, but absolutely can happen in these problems. You can be here and here, and both of those will be defined, and both of those will solve the inequality. What I would suggest to you for this one is go to Desmos and put in this thing on one side and this thing on one entry and this on another, and you can really see how this one will be bigger than this one in these two spots. Okay, anywhere past 5, this will be bigger than this, and anywhere in that little region, this will be bigger than this. All right, super quick little question here, but super important. So explain the difference between f of x, all of that to negative 1, and then it's hard for me to say it and not just say what it is, but explain the difference between this notation and this, and use a function to highlight the difference. So let's take y equals the cube root of x as my function, all right? So this one is what we call the reciprocal. And for the reciprocal, it would literally just be 1 over the cube root of x. That is what f of x, all of that to negative 1 is. You really do just move it to the other side of the fraction, okay? This one, though, this is that thing, the inverse. And for an inverse, you can do it algebraically where you switch x and y and all that, but hopefully we also just know that the inverse is going to be x cubed, right? That's the inverse for a cube root. But one of these is a name. This is a naming mechanism, whereas this one is an actual operation we do in math. So you've got to be careful about that. They look really, really similar, but they're really, really different, okay? All right, just one more little example, just because there's kind of a little trick in this one, and it hasn't showed up in any of the other problems yet. So simplify, easy enough question, but there is like a little trick that I want to make sure you don't forget about. So we got the same root, so we could combine these with multiplication. So 9 times 9 is 81. A to the 9th times A to the 3rd, you would add them and you would get 12 of those. We don't have any b's to do anything with, so we'll just leave that. Then go ahead and do, let's just take the 4th root. So 81 to the 4th is 3. And then a to the 12th raised to the 4th, you would do 12 divided by 4, right? So you would have 3. And then b to the 4th raised to the 1/4, you would cancel off there and you just give b to the 1st. And so it's really easy to write 9a cubed b as the answer to this problem, okay? But it would be wrong. And you should think about right now why that would be wrong. Hopefully you did, because now I'm about to say it. So the issue is probably one of the most important things in this whole unit. And you can go back and look at videos on it, but basically we talked about how if the square root is not a good inverse, and even roots in general are all not good inverses. If you ever square root, like x squared, it is not equal to x. The square root of x squared is equal to absolute value of x. And that's just because if you do like -9 squared in there, you're never going to get the -3. The square root of -3 squared is going to be, like these do in a sense cancel, but it equals -3 with the absolute value, which is 3. Okay, and that's just to maintain the behavior of the even roots as functions. Okay, so if you ever do something like we did here, when we do the 4th root of 81, that truly is 3. But right here is an example. When you do a to the 12th and then raise it to the power of the 1/4, you need to slap absolute value bars on that. And then again here, you need to slap absolute value bars on that. So we could just do like that. Also 9 is positive, so actually we could stick them around the whole thing. Yeah, so if you ever doing that, it doesn't matter if this was a 6 and this was a 6, that still wouldn't be equal. If this was a 6 and 6, you would put absolute value bars. You need those, okay? Super simple thing, but really easy to forget too. Try not to.